All right, so if that's my background, then I need some equations, and the equations are here. I have equilibrium equations, which are these three equations, not including the body forces. Or the same equilibrium equations can be written in terms of the forces Nx, Ny, and Nxy forces per unit width, and the bending moments, and the shear forces Qx and Qy. These are out-of-plane shear forces. So either this set or that, not both. Not necessarily both. The stress-strain equations, which for a single ply would sort of look like this, and notice I'm including the out-of-plane. In this case, I'm not integrating through the thickness. Or if I do it now for a two-dimensional case with integrating these through the thickness, I will have my standard classical laminated plate theory ABD matrix relating strains to forces and curvatures to moments. And then the standard strain displacement equations, which are here, and the curvatures here, which combine together with a linear distribution through the thickness Z, or zeta being measured through from the center midplane of the laminate. And you have therefore 17 equations in 17 unknowns, the 3 displacements, the 6 forces and moments, and the 2 out-of-plane shear forces, and then the 6 3 strains and 3 curvatures. So the whole idea is to solve those, and if you eliminate as many of the unknowns as you can, you will arrive into the 3 governing equations of anisotropic elasticity in terms of displacements U, V, and W. And these are coupled because of the B matrix. You see that the B matrix here is always multiplied in this equation by W. So what would otherwise would have been an equation involving only U and V picks up W here. The same for the second equation, which would only involve U and V again, but because of the B matrix, you have this. Finally, the third one, which would have been only a D matrix times W terms. Because of the B, again, it brings in the U and V's. So for one thing, if we're trying to make our life easier, we should use symmetric laminates because the B matrix is 0, and that would make this to have no U and V dependence, and these two to have no W dependence. But good luck solving them anyway. It is extremely difficult, obviously. And there's a variation of those equations if you include, basically, if you're trying to do a buckling analysis, you have to include some kind of first-order effects. And briefly mentioned here is how you would do the force equilibrium in the Z direction. And the book has complete derivation, or in much more detail. Basically, if you look at this equation at the bottom here, I have the D matrix with the force derivatives of W, and those are the same. Whoops, wrong way. That is the same equation here. If my B matrix is 0, then I will only have the W dependence. But in a buckling kind of problem, I pick up terms which involve my Nx, Ny, and Nxy with derivatives of W, plus my usual out-of-plane loading. Pz is the load per unit area, and then Px and Py loads again per unit area in the X and Y direction. The actual details or first steps for determining that equation are shown here briefly. The book has much more detail on that.